So everybody got the link to this Google Doc file, right?
Yes.
Yes.
Okay, and you copied that in
Yes.
your, and the code was working, right? So far, what we have done until now.
Yes.
Okay, so we can proceed. So yesterday we estimated the FFT, and the next step is to define some new variables like Fn is equal to 1 over, I don't know, did I, oh, let's see if I already defined ST or not. Yeah, so we defined them here. Then 2 multiplied by ST. Then I'll copy this when I'm done with one section. I'll copy that in the Google Doc file, and then you can copy that. I mean, it's better to type it when I'm working, but if you are lost, then you can simply copy that from the Google Doc file. Then another variable df, which is 1 over, oh, unfortunately, okay. And multiplied by ST. Okay, this is df. And then, so we define the frequency domain that we will, so FSP is the Fourier amplitude spectra. I mean, this is the Fourier transform, actually, it's not a spectra yet, amplitude spectra. But we need also frequency corresponding to this one. So here I define the frequency domain like 0, starting from 0, then df. So df is the step size in frequency, and we continue to fn, but one sample before the end, and we transpose it, and that's it. Okay, if I run the code, so at least we didn't get any error. And here fd, you see that this is fd, this is our frequencies. This variable contains our frequencies, and it starts from 0 and ends at about 100. Okay, then okay, here we write the speed is equal to FSP, which is here, the result of the FFT, and we just take the first element up to the last one. And then divide it by 2. Okay, this is SP. Then we open a figure. Oh, let's take the absolute here, and then it will be amplitude spectra, and let's call it FA is equal to ups of SP. And then we open a figure here to plot it, and we use log. You're already familiar with that. So the X here is the FD, which are the frequency values, and the Y is FA, the amplitude spectra. And let's use red marker to do that. Okay, thanks. We got an error. Oh, I didn't run this part, sorry. So this is our Fourier amplitude spectra. Let me copy this part and append it to the file. So from here, these are related to today. So can you see that online on the file, on the link that I sent you?
Yes.
Okay, if you didn't type it, you can simply copy that to your M file. Okay, and yeah, so this is our Fourier amplitude spectra, and then let's write grid on, and if I run just this one, so you see that the grid lines have appeared here. Then let me here. Then so here we have the Fourier amplitude spectra, and I now want to introduce you some comments, because we need to select the lower and higher cutoff frequencies where we think that the noise is dominated. You probably remember it from the lectures, the last classes, that we were talking about processing strong motion data. So we know that usually at short periods or very long periods, or high frequencies and low frequencies, the noise will be dominated. From simple source theory, we know that the slope of this trend over here should be about 2 in logarithmic scale. Okay, so we say that this trend is what we expect from simple source theory, and from here it's deviated from the trend that we expect. So probably there is the noise is dominated at frequencies smaller than this value, about 0.25. Okay, so we want excuse me, we want to make this code sort of interactive, and it's quite important to do that, to make it easier to use. So we can write here. So are you done with that? Everybody has this figure?
Yes.
Yes.
Yes. Yes.
Okay. Yeah. So I'll open a new section here, and so we want to make it interactive somehow. And it's one of the beauties of Matlab, that it's quite simple. So first of all, we write, let me put a CLC here to clear the command window. And this command window is where you can show your comments or ask for inputs or whatever. And let's write a message to the users here, and let's say select the lower corner, for example, frequency. Okay, and then in the next line we will display another message, and we can say, for example, then yeah, so and then press enter. Okay, if I run this part, these messages will be appeared on the command window. So you are saying the user, or if you are the user, that what to do now. Okay, so then we ask the user to select their lower corner frequency, or maybe it's better to call it cutoff frequency. Okay, but how the user should do that? Let me copy this one. Okay, you can copy that from here. And let's run the whole code again. Okay, the figure is here. This is the first figure, and this is the second figure that we produced. And we ask the user to select the lower cutoff frequency and then press enter. So how should the user select the lower cutoff frequency? There is a command called G input. It's quite straightforward. Okay, and what G input command does is that the user can select a point on a figure, and the coordinates of that point, for example, this point, its coordinates, its x is, or frequency, 0.2, and its y is 1.35. Okay, so J input will store the coordinates of the selected point on a figure. This is how it works. But we didn't run it now, so we use G input and we save. We don't need the y coordinate here. We just need the x coordinate because we are looking for frequency, not for the amplitude. And we call it, for example, we can say LU underline, I don't know, corner, something, whatever. And for the next one, because we don't need it, we can use this. Okay, then if I run the code, I guess we got an error. Why is it interrupted? Let me run this part. Okay, and then this part. Okay, you see that the cursor has changed. Now it's ready to select the point. Okay, so what I did here is that I didn't put any argument after G input. So it means that the user can select many points as I don't know, 10, 12, whatever. So it allows the user to try. For example, you suddenly click here by mistake, okay, and you will select a point, and let's try it. Let me just see, and let me copy that. It's better to, okay, here. And so we don't, when we are opening this figure, we don't need the time series. We can close that before. Oh, sorry. Close all should not be here. We already closed the figure. Where is the time series? It's So this is where we plug that. Okay, we can add it here. Okay, so you see that the Fourier amplitude spectra is plotted and a message is written on the command window asking for a cutoff, lower cutoff frequency. And for example, we can select it here. And I don't know why it's not working, because the desktop is shared or what? Okay, yeah, it's working. Okay, and as you see, I clicked so many times. I don't know, 1, 2, 3, 4, 5. I clicked 5 times and then I pressed enter. So then we also need a high cutoff frequency, and we can copy this to here. But here we ask for higher cutoff frequency and then press enter. Okay, then we also rename this variable and let's call it HU corner. Okay, and if I run the code, let me copy this. So everybody is following me, right?
Yes.
Yes, yes.
Yeah.
Okay, I guess this Google Doc can help a lot. And then if I run it again, I got the figure, I select the lower cutoff here and press enter. So you see that it appeared here. And also I can select the, let's put it here. No, for example, here. And press enter. So did you see that I tried 2 different points and both of them are here. So, but the point is that we just need one low frequency and high frequency cutoff errors. So what we can do is to select the last point. So how we do that, we can say, so let me open a section here because we are done with the interactive part. And then we can, let's say this. So this refers to the last selected point in LU counter. If it's more than 1, then it will be the last one. It will refer to the last one. And we will save it in a new variable, and let's call it a corner, for example. And also we do it the same for this one. Let's call this one also H corner. Okay, so this can be here. It's better to keep it there. And let me also copy that. Okay, when we run the code and we select the lower enter, I put it here, you can see on the command window that what's going on. And then, for example, here and enter. And you see that these 2 are selected. They are the same as these 2 because I just selected 1 point. I did my best, and the best one was already selected. And then, so here we go to the, let's call this section filtering. There are very good filters already defined in Matlab, but I'll write a very simple filter here, but you can later on use the other filters that are incorporated in Matlab. And so we need a character, a variable called role, then we can define our filter. Let's call it L filter. And so it should be FD. FD is our frequency values with power of 4 multiplied by enroll L. Then we will divide all the elements by FD, again with power of 4, and let me use this one, then I can enroll L, and then we add it with L with power of, again, the same here. Okay, so and we'll close, we will put a semicolon because we don't want to print all these values on our command window. Okay, so then this is our filter, and we will plot it later on to see how it looks like. This is actually the one of our filters. So we first use this one, and but wait, so why don't we first start with the high frequency? Just keep it here, and we already defined that one. And let me also introduce this one. And okay, and H filter, for example, is equal to 1 divided by plus, and then here I put frequency and divide it by this one, and then I will use this power, which is 4 multiplied by enroll H. It's quite tricky to use all these parentheses. So what I usually do to make it easier for myself is that when I open a parenthesis, I close it immediately. You know what I mean? Then I cannot get lost. And the other point is that, for example, if you click here, you see that it shows that this parenthesis opened here is closed here, or this one is related to this one, or this one is related to this one. Okay, so this is our filter here, and let me copy this one here. I hope it's working. I didn't try it, but okay. So, and then this is our filter. We will plot it later on to see how does it look like, but then we simply multiply. Let's define a variable, call it SP, for example, age filter is equal to, so we multiply the filter that we made to our amplitudes, right? So the filter is this one, and we multiply it to that. Okay. So we can, this is already here. Okay. We can type hold on, and we will plot the filtered on the same figure to see how it has affected our Fourier amplitude spectra. Okay, so we use command again log. This time we will, so frequencies are in FD and the high path filtered values are here, and we use, I don't know if we are, okay, we used to use also apps, because if I'm not wrong, we didn't use apps here. SP, no, apps is used here, so we need to use apps to take the absolute, and yeah, that's it. Okay, let me, oh, and we need to specify another color to make it visible, so we will use dashed line and green. And if I evaluate that, okay, we got an error. Don't indexing is not supported for variables of this type. What does that mean? Where is the error? Let me hold the code. Okay, we got an error at line 110, which is here. Oh, what is this? This should be dot and multiplication. Okay. Let's run whole code and select the just the lower cutoff frequency and some upper cutoff frequency, and that's it. So this is the low pass filter. Okay, the red one is our original FAS, and the green is low pass filtered FAS. Okay, so we also defined another filter here, which is high pass. Okay, and then we, so is it correctly? Okay, I guess it should be correct. So we will use this one, the green one, and we will high pass filter it. Okay, so this is what we are working on. This is the low pass filter. We want to high pass filter this one, so we will multiply it by our high pass filter, and we will store it in a variable, and We'll give it an appropriate name. For example, I don't know, ESP-LH. LH means that it's low pass and high pass now, and then underline filter. Okay. And if I run it here, okay. At least I didn't get any error till now. And I want to, so it hold on is already there. So I don't need to use it again. And this time, instead of this one, I'll use this one. And we can also change the color or marker or whatever. Let's use dash dot dash. Okay, yeah, we can use a dash that and then the color blue. Okay, and if I run this part, this is what we like. So the red was the original, the green, which is now beneath, this part of the green is beneath the blue one, but this part is clear. The green was low pass filtered and the blue is low pass and high pass filtered now. Okay. So I need to update this one, I guess, all the filtering part. And, okay. I guess, okay, I don't need close all now. If I run it, this is the code. So this is the window, the first window, but we are going to work on this one. So we select this one and press enter, and then select this one and press. Oh, I guess something is wrong. Let me. I guess it's because two figures are open. Are you guys able to do that, or you're also experiencing the same problem as me? Hello?
No, I can select the two frequencies.
Oh, even if your first figure is open, right?
Yes, yes.
Okay, by the way, so let me do that and press enter, and then this one and press enter, and this is what we will finally get. So everybody is able to do that?
Yes, yes.
You do.
So I need all your approvals, please.
Yes, yes.
Okay, Tariq, I didn't hear you, I guess.
No, I told you yes.
Okay.
For me, my machine is still running.
Still running.
Yes. I don't know what's wrong with this machine.
Why is that? Okay, if did you copy everything from this file?
Yes, everything. And
so which part of the code is that? Which part is stuck? Can you?
When
so can you share your screen, because it could be also good for the others to learn how to debug that.
Yes. When
stop sharing. Oh, are you?
I'm coming.
Okay. I hope that you are not going to use your webcam to show it to us, but
oh, is that one?
okay, let's see. Oh,
can you see? When
it's not very clear. I want to see the command window.
Okay.
So what is the last, oh, it's very difficult. I cannot. What is the last thing that has popped up?
Where it started was where we were selecting we're doing the filtering.
Okay, this is where the code is stuck, right?
Yes, yes. It's still running. The program is still running.
And you didn't get any error.
No, I didn't get any error. The program is running and it does not stop running.
Okay, just press Control C to see
Okay.
where it will.
Yep. I've terminated it now.
So which line is the program killed? What's the error that you get when you kill the program?
I said operational or terminated by user during J input to line.
So come on, no, this is G input. This is where the computer expect you to select the low and high corner frequencies. It's not running. It's just waiting for you. And it shows you have to run it again and just pay attention to the message that you will see on the command window. So before that, it's written on command window that, okay, you need to select low frequency and high frequency and then press enter. Just do what I exactly do. Please stop sharing. I do it one more time and just pay attention to the things that I'm doing. Okay?
Okay.
Stop and share. Okay, take a look. I'll run the code and this figure will pop up.
Okay, let me run it.
My cursor is something like that. Okay, and on the command window, there is a message.
How come my cursor is not appearing like that?
Okay, do something. Let me kill my program. Okay, add one close all command just after processing command.
I should
like
add what?
That.
Close all command after processing all command. Okay.
After this one, after this comment line, just add a close all command. Okay.
Okay. Let me process. Yes, I've done it. I should run it.
Okay. Yeah, run it again. So is this message appearing on your desktop? On your command window, select the lower cutoff frequency and then press enter. Is it there?
No. Now it's giving me some errors. I'm coming, creating a string using the vocal.
Oh, you got error.
Yes. Okay, I'm coming. Let me delete this stuff from it.
I guess it would be far better if you copy everything again from this file.
Okay, let me delete everything and copy it.
Let me update it with mine exactly, and then
Kubu, inside log you don't use double price, you have to use on, because the job version, job version different compared with professor. So inside log and space.
Inside what?
Okay, I will write on.
hello. Just copy everything from this file to your M file.
Okay.
Then you don't have then you will not have a syntax error at least.
Okay. Yeah, I think Dung was saying something. Let me, because I'm using log, not log. Okay.
I mean, use exactly the same command. They're all copied there. So it's
I
quite
think, Professor, the thing is,
Yep.
the issue is my version is different from yours. So there are some.
what's your version of Matlab? It should not be
2016.
I guess it should not be a big deal.
Yes.
Okay, just copy everything
If I copy everything, I have to make a lot of changes again because I was making them whilst I was copying.
okay.
Yes, I was making those changes whilst I was copying. I remember. So if I copy everything, I have to do those changes again. So
okay, just try it. Okay.
Do have sent me some this one. Let me follow. I think she's using the same version. So let me follow.
Okay, so you can do it and let me know later on if you're done with that.
Okay.
So let me do it again. I select this one. No, it was not good. So I select this one and then press enter and then I select this one. No, I'm not happy with that. So I can select this one and press enter and it's done. So this is it. And what else we can do? Okay, we want to, so we already defined two filters here. One is saved in variable H filter and the other is saved in L filter. So we want to take a look at them and see how they really look like. So we open a figure here and we simply plot them again with log FD is our frequency values and then L filter. And let's plot it by red. Okay. And then hold on. And again, log FD and H filter. And we can plot it by E. Okay. So this is how our filters look like. The blue is the low pass filter and the red is high pass filter. You can probably not see that very well. So we need to change the access limit. So we can say xlim. You're already familiar with all these commands. We can put it from, I don't know, 0.10 with power of -2 to 10 to power of 2. So it's from 0.01 to 100, right? And then ylim, we want to extend it a little bit. So we can, this is good, 10 with power of -12 is good for the lower limits, -12, and then instead of 1 here, we can put like 10, just, okay. And if I evaluate that, you'll see that what's going on here. So this is our simple low pass filter shown by blue and our high pass filter shown by red. And if you just take a look at these two figures, this is what we multiply to our original FAS. Okay. So if you remember, let me close this one and I guess we need to copy this also. Oops. Oops. So this is the comment. Everybody plotted also the filters.
Just
Okay,
Yes.
Yes.
but
Yes.
we can comment them because it was just to check it out how it looks like. We don't need it, and we are not going to select that. So we already know what are the input and output values. So I'll comment this one and this one, and I'll simply put the values here. For example, LC was something about 0.3 and oops, this one, let's put it at 30. Because I commented that this part, the interactive part for selecting, because we are not going to select it every time. So we did it once and we know what are the values, and then we just run the code. And also I'll comment this close all because I want to show you some other stuff later on. So this was the acceleration, velocity, and displacement of the original an unfiltered file, and in frequency domain it was this red trend. Okay, now we have filtered our time series, and we want to see how the acceleration and velocity and displacement will be in time domain, the filtered one, the corrected one. Okay, so one way to do that is to convert the filtered acceleration spectrum to time domain and integrate it once to get the velocity and twice to get the displacement. But there is another way to do that, and it's like integration in frequency domain. Okay, and we can try this one as well. So instead of integration in let's call it this section, instead of integration in time domain, you can simply do it in frequency domain. So you don't need to use IFFT to go back to time domain and then integrate in time domain. So we call this section like velocity in frequency. Okay, so first let's take a look at the velocity and displacement spectrum of the original time series. So we can define here an omega or W, which is 2 pi multiplied by our frequency. Okay, this is omega. And then we define FV, which is FA divided by W. So this is similar to integration in time domain. If you divide your acceleration in frequency domain by 2 omega, this is omega, or by 2 pi frequency, then you will get the velocity spectrum. And when we simply open a figure and plot FD against FV with, I don't know, red marker. And yeah, so let's run it. Okay, this is velocity spectrum of uncorrected record. Okay, and then what else we can do?
Professor,
Yep.
in omega 2 pi multiplied by FD.
Yep.
FD is the frequency, yeah?
Yes. FD
And-
is frequency vector that we defined here.
Yeah. And FA, what is
FA is the FA is absolute of the output of the
Fourier
FFT.
transform? Oh, okay,
Yeah.
okay, okay,
But just the real part.
okay.
Okay, so this is it. So we want to compare this one, which is velocity spectrum, with uncorrected, with the corrected one. Okay, so we can type hold on and then log, and so FDs again here. And you remember that this was the corrected acceleration spectrum. Okay, and if we want to convert it to velocity, we simply need to divide it by W. Okay, we need apps of this one and then divide it by W in frequency domain, and let's show it by dash dots and blue, and I guess it was here. Okay, and if I evaluate this part, you'll see that. Okay, this is the corrected velocity spectrum and this is uncorrected. And to make it somehow nicer, we can add X label and call it frequency. Also, okay, read on, for example. Okay, so this was in frequency domain, the velocity in frequency domain. Let me copy that here. Cool. I guess you did you also change? Let me update everything. Okay, we can also take a look at the displacement in frequency. So how to do that? It's quite straightforward. We have FV here, then we can divide it by omega again, right? So we can say FD is equal to FV divided by omega, and figure and again log of FD capital. with red and hold on. Okay. But here, instead of division by omega, we can divide it simply by omega with power 2. Oops. And is something wrong? Oh, I didn't put this one. And if I run this part, so this is our original, the red one is our original unfiltered displacement spectrum, and the blue is the corrected one. Okay, so I guess I need to copy this one as well. So everybody did this stuff, or yeah?
No. That means still continue the same view.
Oh, you got, sorry, I didn't hear you. Don't.
I mean, I got it.
Oh, you got it. What about the others?
I've got it.
Okay.
Me too.
Still running.
Yeah, I've resolved
Okay.
the error.
Oh,
Yes.
you, okay, perfect. Then, okay, we want to return to time domain to see how the, let me show you here. Okay, this is time series and this is figure. And this one, and this one. Displacement. Okay, this was our original time series, but we want to see how we want to return to time domain to see if these problems with time series in velocity and displacement are solved or not. So to do that, we can open a new section here and okay, call it by FFT, and we can define a loop starting from okay, starting from oops, 2 to what was the variable, not offset or something. So we are okay. This one and divided by 2. I can close the end, the for loop here, then it's quite easier for me. And then an important point is that when you are writing a for loop or if, just try to indent the code, then it would be much easier to read. For example, if I write a code and inside a for loop, I write something here, it would be very difficult to follow that. So at least press a tab and start from there. And even if you don't do that, and after for you press enter, it will automatically indent that. It's quite important because when you want to read your own code, at some point it's maybe impossible. So let's put SPLH underline filter, if I'm not wrong. Yep. And again, this variable and divide it by the counter here. Oops. I mean, for not the division. So what we are doing is to trying to add the real part again to be able to do the FFT. So later on, when you read the code, you will realize that what we are doing here. And then here, we already have the real part, but we need the conjugate part. So this is the command conj. Okay, if you write it here, help conj, you'll see that. It's complex conjugate. And conj of what? Conj of this one. Of I. Okay. This will make our a spectrum including real part as well as the conjugate part. And then we define a variable and let's call it new time series. It's quite straightforward here. We use IFFT command and our new spectrum here. And we will multiply it by sampling frequency is F. That's it. I hope that it works. Okay, so no. Oh, I didn't run all the code. So the variables were not there. Okay, we're done. Let me close this one because we don't need anything in frequency domain anymore. And then, so this is our new acceleration time series which is filtered. And we open a figure, and again, we use the same format that we have used here. So we use subplot, for example, subplot. It's 3 by 1, and the first one would be plot time series. This is our time axis that we already have it, and we detrend it again here. Detrend our new time series. Oh, let's do something else. We don't need this figure. We can plot both of them. This one. So this is our unfiltered time series. Okay, and we'll plot it by red. Okay, then hold on, and we will plot our filtered time series, and we will superimpose that, and in this one will be here. This is our new time series, right? But the point is that if you remember, we already padded the time series. So we found the next power of 2 here, and the difference between this one and the length of our time series was padded. So we added zeros to the end of the time series and to the beginning of that. Okay, so we need to remove those pads now, those zeros from the beginning and from the end of the time series. And so if you remember, then the length of the 0 vectors was npad, and we will plus from 1. So this is where we begin to plot, and we will continue. Let me put some space to make it easier to read. So this was the variable that was the length of our time series was in this. And we will add it again bit by npath. Okay. And let's use, I don't know, another marker like this one. Okay. If I do that, I'll get this one. So there is a red one behind this, but you cannot see that. Let me plot this for. Okay, this is our original. You see that? And this is our filtered one. So the difference is not that significant. But let's say what happened to the displacement and velocity. Are you guys still with me? Can you hear me?
Yes.
Yes, yes.
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 Are you following the procedure, or oh, I forgot to copy the things there. So where we were last time, displacement in frequency, IFFT. Okay. I updated the file, the shared document, so we can also. Okay, so this was acceleration, and let's see what happened to the velocity and displacement. So we will plot the displacement subplot in the second subplot. So it was 3/1 and the second one, and we plot again. So this is okay. We plot time, which was in the first column of time series, and our velocity, I guess we stored that somewhere in a variable called vel, or this, if I'm not okay, vel. We trend vel, using red marker. So hold on. And, okay, so this was our corrected acceleration, filtered acceleration in time domain, right? Hello?
Yes.
Okay,
Yes.
so what we can do is just to integrate it. We can do some other stuff as well. We can, so we have the velocity spectrum here, and we can do the IFFT and convert it to time domain, or we can also, for the displacement, we can do this one as well. But another way is to just use numerical integration in time domain to get the velocity and displacement straightforward from corrected acceleration. Okay, so we define here something like fvel, and we use again com traps. Okay, and what? Okay, we need time again. Time is the first argument. And let me put a semicolon here now. And then what? Okay, and then our time, new time series, which is this one. Okay, so this will be our new velocity, hopefully. And then we can plot it again, plot this one. So yeah, this is our time. Then F12. And so those zeros are already removed before integration. And so we can also detrend it again. Detrend is quite cheap and you can always use it. And we use the same marker for this. Okay, perfect. So the red one was uncorrected velocity, and the green one, the blue one is the corrected, the filtered one. And you see that, okay, now it looks like a waveform. Then this is updated, you can copy that. And let's go to the displacement subplots. 3 by 1 and then the third one, and plots times 3. The first column was time, right? And we already have the old the displacement in these, and let's the trend this and plot it with red. Then hold on, and again, everything should be repeated from here. We define something like f this and traps time first column, which is time, and then so we don't need to do anything with acceleration anymore, and we have the velocity here, and already the zeros are removed. Okay, we can simply take the integrate, we can take the integration here, and that's it. So let's also plot this one again, times 3, the first column, and F this, and we'll use dot dash b to do that. And yeah, but we will probably not be able to see anything of the new one, because if you remember from, if you remember here, where is that? Let me plot it again here. I mean, you should not be surprised to, if you plot the original time series and then you superimpose the new one, you will not see anything, because the displacement range here is up to 200 centimeter, which is too large. Okay, so we will try it, but finally don't be surprised if you cannot see the new one. And okay, let's try this one. Yeah, as I told you, it looks like a flat line. So what we can do, so you already see that it's corrected. Of course, this cannot be, the red one cannot be realistic, and the blue one should be good. So let's zoom on this part that the new corrected one is located. So we can simply use ylim command, and we will, oops, I made a mistake. No, okay, it's fine. So we will limit our axis, y-axis to the minimum and maximum of our corrected displacement. Yeah, okay. You see that it looks like it looks far better, but we still have this linear trend, and you can simply kill this linear trend by this command, by detrending that. Oops, what happened?
I think that you've missed one E in the trend.
Oh, did I?
Yes.
Okay, yeah. And it seems that it's a real command because I didn't get any error. Okay, let's try it again. Yeah, that's it. So, yeah, so I guess that's enough for this one, and I guess we reach to a good point. You already wrote a code, and the most important point is that your code is interactive and you can use it. I mean, these simple commands like g input or all these commands to write your own code to do the things that you want to do. And many times in this code are really unnecessary and so many gaps, but the code is less than 100 lines. So in less than 100 lines of code, you can do such amazing stuff. And for example, you can let me I don't know how. We have 10 minutes, and I guess 10 minutes is not enough to do anything else. Okay, so let's talk about GitHub and some codes there. So I don't know, did I update it, the last comment or not? Let me. Okay. Yeah, this is updated. And so are you familiar with GitHub?
Yeah, just.
Okay, so just go to this. I sent the link here. The last line. Go to this link. Everybody did it? So this is an example of a simple Matlab code in GitHub for producing shake map. The simple algorithm behind that is in this paper, and you can see that this is the paper. This is the paper, and it's already on GitHub. When you download the code, you can also have access to this paper. And here is the algorithm for producing PicMap. I know that Leticia already told you about PicMap, about shake map. And
Yes.
this is also a very simple code for generating shake map in Matlab. And you can download it, download the code from here and unzip it, and there is a sort of README file that explains everything, and you can also try to manipulate that one, and yeah, just play with that. But I guess for now you have a good background in Matlab, and you know so many useful codes, and you already we wrote an interactive code that's very important code together, and so you can consider it as a starting point for writing your own codes. And yeah, that's it. So we still have 10 minutes and I want to use that also, we don't lose any time. So let me share my Matlab window and introduce you some new commands. So can you see my command window?
Yes.
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 Okay,
Yes, we can.
perfect. So do you remember we already introduced the dir command and everything, right? The command dir. So we define a variable. So where we are in PWD, and we define a variable CDR underline dir, and we already did it, I guess, in the first day, and here we will use it in some. We can, for example, we are looking for some specific file. Okay, you remember that we saved our time series in .mat format and in binary format, and I told you that the .mat is a sort of binary. It's a sort of binary, and it's very good for saving large figures, okay, or large files. So we are looking for everything in the directory that starts with time series dot, and it doesn't matter what is the extension, okay? And so here we are. Oh, I didn't use the command dir. Okay, this is what we will get. Clear everything, and okay, and then this is what we got. Oh, I'm always making this mistake. Okay, it found 2 files. And then let's practice some other stuff like a for loop I equal to 1 to length of CD CDR dir. So we want to see the size of these 2 files. Then CDR. First, we want to see their names. Okay, then we can recognize that which name, which size is related to which name. Then I, then dot name. Okay, then we also want to see the size of each one. So this one should be, if I'm not wrong, bytes or byte, the field. Oh, let's try with bytes. And then we can also display something like that to show that this is the first one and this is the second one. And end. Hopefully it will work. Okay, perfect. So this is the file that we saved yesterday, I guess. And this is .mat, and you see the size is much smaller. I mean, these 2 files contain the same information, but the size of the mat file is about 1/5 of the usually ASCII, I mean, the ASCII text file. So this is another practice, and okay, so I guess we cannot do anything else. So do you have any questions? Please ask. Hello?
We're here.
So any questions?
Just a curiosity.
Okay.
In the code that you showed us, PicMap,
Yeah.
what kind of interpolation is used?
Yeah, that's a good question actually. So let me show you. Actually, I wrote this code, I don't know, maybe about more than 10 years ago. So myself, even I don't remember the details, but this code, there is just one part for numerical interpolation. And this is I mean, one of the last steps. And if I'm not wrong, I used a spline. Yeah, a 2D spline interpolation is used, a 2D spline. So the numerical, if you are talking about numerical interpolation, that's 2D spline. But before numerical interpolation for generating regional shake maps, we do lots of other stuff. We apply the GMPs to predict the values in PGA values or spectral values in phantom stations and everything. So if you are interested about that, you can just write this paper. I mean, read this paper. It's quite short, and the paper is also on the GitHub address that I sent you. Okay, any other question?
Okay, thank you.
You're welcome. So, hope that these were useful for you, and if you have any questions later on, just don't hesitate to write me, and yeah. Okay, thank you guys. Bye.
Okay. Thank
you.
you very much.
Thank you.
You're welcome. Bye.
Good
Bye.
morning.
Bye.
Good morning.
Hey.
Good morning. Hey, Innocent. Where is Kumsa?
Lost
Hey,
contact.
Haroon. I don't know for
You
sure.
always leave the meeting right after. I hope you are fine. Everyone is doing well.
Yeah, sure. Yeah, fine.